A warm welcome to all. So, my name is Shankar,
My name is
and
Balamurali.
we are doing our final year project on standard cell based processor design using MGDI technique, and it comes under the area of VLSI. So, let's dive into it. So how we are going to do it? The methodology is so we have two parts mainly, custom design and semi-custom design. The custom design includes the standard cell creation, which we will be doing in Cadence, and the semi-custom design of the RISC-V processor that we are going to implement will be done using RTL code, and it will be functional verified. And combinedly with what the standard cells that we have created, we are going to use that for that RTL coding, and we will analyze various parameters like power, delay, and timing, etc. So next slide. So this is a MGDA technique that we are going to use. Uh, so basically, as you can see, the input can be connected to either the source of PMOS or NMOS, or the gate terminal of the uh, NMOS and PMOS. So, but the body is always connected to body of PMOS connected to VDD, and body of NMOS connected to ground. So this is the basic structure of a MGDA technique that we are using. So next slide. Uh, so these are the cells, that basic cells that we have done using the MGDA technique in our cadence, and use these as standard cells for our processor design. So let's move to the cadence part. So I'll be sharing my screen. So as you can see, this is the tool that we are using. So it is Cadence Virtuoso. As you can see, to just for an example, I have taken a GD8 technique, 2 cross 1 mux. This performs a multiplexer. This acts as a multiplexer, 2 cross 1. So A, B are inputs and C is a select line. So this configuration acts as a 2 is to 1 multiplexer. So after designing the schematic of a cell, so we perform the pre-layout simulation and obtain the power and delay report, delay thing. And after we did that, and whether after seeing that it is correctly performing, the functional verification is done, we go for the layout design. So layout design is where uh, we connect metal to NVL. So overall, how the standard cell should be if it is designed. So that is how what we did using the layout. So after doing this layout part, uh, we take perform DRC and LVS. DRC stand for design rule check, which ensures that there's a minimum spacing between the metals and wires and metal to metal distance, and so such that it will make sure that there's no overlapping, something like that. So that is DRC, and LBS is layout versus schematic. So the schematic that I have done here, whether the layout that I have put, uh, whether these both are matching, that is checked by this LBS. So layout versus schematic. If both are matched, then we'll go for RC extraction. So uh, RC extraction uh, will show a result something like just a second. So it will have actually the inbuilt the layer that we have designed. The resistance and parasitic resistance and capacitance value will be added after we uh, did the RC extraction. So that is the step that we have to do after layout design. After extracting the RC values, We will be going for the post layout simulation. So if I select and descend read, if I click, it will be pointing to the AV extracted view. So the AV extracted view is nothing but the uh, RC extracted version of the layout. So this symbol is pointing towards that RC extracted values of the layout. So thus providing accurate powers and delay. So that's the thing. And after creating symbol like this, so for many cells, we will be doing the same thing, which I explained before, and we'll be putting all the uh, symbols in a single schematic, and we'll perform ADL launch ADL, and in this we'll go for simulation, netlist, and create. So if we do this thing, so we'll have a netlist of all the uh, symbols that we are using. This netlist is used for the lib file generation. That lib file is basically the file which contains the power and timing and electrical characteristics of the cells that we are designing. So, example of a lib file that we have generated is so here, as you can see, so cell name buffer, area, cell leakage power. So all the parameters uh, that are associated with the cell that we have designed, like power, delay, and electrical characteristics, will be put in a single file like this. And this file is used for uh, analyzing the power of the overall process design for the RTL synthesis that we have done. So if you see, like slow.lib is a file. So this lib file, I am like pointing towards that lib file, and I am reading that disk5.v. So this is the Verilog code of the RISC-V processor that we have done, and I am reading elaborate synthesize. So it will synthesize their uh, Verilog code. So synthesis happens. This is actually Cadence Genus. With the help of Cadence Genus, we have done the synthesis process. So we analyze power, area, and delay by using this genus, and that's the thing. And moving back to the presentation, so Paula. So, like I said, like the pre-layout and post-layout simulations that we did for power, as you can see, the post-layout simulation is done with the RC value included. So the parasitic capacitance and resistance values included. So we'll get a slightly increased power. Like if you see inverter 2.99 watts, and in pre-layout and in post-layout it is 3.39 watts. Similarly, for all the cells, there will be a slight increase in power. So next slide. And similarly for delay, also pre-layout simulation, if you see, like 7.87 picoseconds for inverter, and post-layout 10.70 picoseconds. So there is a slight increase in delay. So this is due to the fact that the RC extraction has been done successfully. So next slide. And we have made a comparison between the static CMOS, which is the most used logic style, and our MGDI technique that we have done. Uh, as you can see, the uh, delay, you can see like 29 picoseconds for OR gate and 366.53 fermiseconds for MGDA. So, like there's a significant, uh, like MGDA technique is very much better as compared to the static CMOS in terms of delay for every cell, as you can see. So, next slide. Similarly, in power calculation also, like if you can see, or 10.96 nanowatts and MGDA 236.56 pico. So uh, definitely MGDA technique is having better result. But in NAND and NOR, like static CMOS is slightly dominating, but the difference is not much. So the difference is not significant. So it's fine. So next slide. It will be
Uh,
explained by my friend.
so this is the semi-custom design where we take a Verilla code and it has been run through the standard cells we have created. With there will be different modules available in Verilla code. So we have taken that and we have modified to maintain the exact replica of the architecture we have used in the RISC-V processor. So these are the modules that we have used: register file, arithmetic logic unit, control unit, data path, instruction memory, instruction fetch unit, processor design. So these are the modules which we have used in the architecture, and the name in the brackets is the name which we have used in the Verilog code. So coming to the next slide, so this is the basic structure of the Verilog coding we have used. So this will be like very well understandable when I show the live demonstration of the code. So let me show the live demonstration. So we have executed the Verilla code in EDA Playground. So as you can see that this is the register file where all the inputs from the registers and the values to be written to the register and the data, reading data and the clock, everything is inputted through here. And these as the memory is 32-bit memory. Each memory has been allocated to each value. So as you can see, memory of 0, memory of 1, memory of 2, so each bit has been allocated separately. And finally the input has been obtained from the user, and it has been passed through this module called data path v. Data path v is nothing but a collection of all the modules except that register file. So, so as you can see, the first module here is the ALU unit. As many of you know that ALU is responsible for the operation taking place in the processor. And with this there are two inputs, input 1 and input 2, which contains the value. ALE control is which tells what operation needed to be done, and the result and the zero flag. So with this 4-bit value, we will be able to decide what is the operation needed to be done. And based on the operation done with the input values, the result has been allocated. So as you can see, this 4-bit 0000 is depicting and operation. So with like similarly, what and all operations are available, it will be allocating it. And with this data path, and second comes the data path module, where this acts as a bridge between these two files. Actually, as you can see, the same register one read value write register AL control has been seen in the register file dot v I mean register file dot v file. So this acts as the bridge between that register file and data path as it gets the input, and with this input the ALU module has been taken care. And with this yeah and after getting the input from these register file, the ALU module has been instantiated with these inputted values. And next comes the control unit. So as you saw, ALU unit is responsible for the operation. It basically does the operation which comes from the signal from the control unit. The control unit actually tells which function or which operation code, which operation needed to be taken care of. So this function 3 and function 7 tells which operation to be taken care of, and OP code tells that which type of instruction should be taken care. So in this we have used R type instruction, and based on that function 3, I mean, both function 3 and function 7 are used as the operation decider, but function 7 sometimes, function 3 sometimes is same for two operations. So for the in that case, function 7 has been used. So as you can see, function 3 is same for add and subtract, but function 7 is different for add and subtract. So in this case only the function 7 comes into role. And that with many case statements, as you can see, there are very many ALU control as XOR, multiplication, shift right left, shift left logic, shift right logic, and an OR. Yeah. And this is the instruction memory is nothing but as in the architecture we have taken, the program counter value will be increased by 4 after a particular instruction gets updated. So this instruction memory is responsible for the increment of program counter by 4. And after that, here is the 32-bit instruction add, subtract, multiplication in XOR. As you can see, there's one value written here. So that's the maximum limit of value. Like beyond that, there won't be any addition value or subtraction value. So that we have given, so that if it exits this value, it will give an error. And finally comes the instruction fetch unit, where here based on the reset option, the program counter has been incremented here. And the final module is the processor module, where all these modules we have seen till now has been integrated into a single unit for the processor design. So this is the test bench we have used for this code to get the input and to get the output properly. And with after executing this, we have got this output. So for example, I will explain just two or three input and output. So this has been as you can see here, hexadecimal values has been used. So hexadecimal 17, hexadecimal 2a, that is the two values given as the input. And ALU control is 0. ALU control is 0 means ALU control is 0 means it's AND. So if you do bitwise AND between 17 and 2a, you will get the value as 2. So similarly for all operations, we have to do like that. And for another example, I will take as 4. Here 4 is nothing but I think it's subtraction. I think so. If you subtract, you will get as this value. And yeah, that's the output we have got for everything. Similarly, like for every operations, we will get an output based on this value given in the test bench. And going to my PPT. Yeah, this architecture this block diagram I have explained it through live demonstration. So as you can see, we have got the output there. And with this Verila code, we had a set of standard cell being used. So with that standard cell created, and with the Verila code, we have obtained the total power, delay, and area of the whole module. This as you can see, the power is 30.00022 megawatt with required number of standard cells. And with this increased number of standard cell, we have added some new cells such as buffer and 3 input NAND and 3 input NOR. So as you can see, with increased number of standard cell, there has been like reduction in power and delay. But obviously the area will be more because this number of standard cell has been increased. So with this, the future scope is that when we increase the number of standard cell, the value of power and delay will get reduced. So that with the maximum number of standard cell created, we can reduce the power and delay to the maximum. So these are the references we have used for our project. And thank you.
Actually, the power is milliwatt.
Yeah, milliwatt. Sorry.
Okay.